Good afternoon. Our guest today is Dr. Alfio Torrisi. He graduated in physics at the University of Catania in 2013. He obtained the European Research Doctorate in Optoelectronics at the Military University of Technology in Warsaw and at the Czech University of Technology in Prague. During his PhD, he developed several prototypes of compact microscopes based on gas puff target sources and operating in the field of soft X-rays and extreme ultraviolet. In 2018, he was associate researcher at the University College of London, collaborating with the Advanced X-ray Imaging Group at the Department of Medical Physics and Biomedical Engineering to develop a microscope for medical investigations of tumoral tissues. From 2018 to 2020, carried out his research activity as postdoc at the Nuclear Physics Institute of the Academy of Sciences of the Czech Republic, using the beam lines of the Tandetron accelerator for applications to material science, biomedicine, cultural heritage, and applied physics. Since 2021, he has been working as a junior researcher at the University of Salento, the Department of Mathematics and Physics, Ennio De Giorgi, and at CEDAD. Dr. Alfio Torrisi is also involved in the study of the interactions of radiation with matter and the characterization of plasma produced by lasers, and in the technique of the use of low high-energy ion beams, electrons, photons, for the treatment of materials and their characterization. He has also established several international collaborations, contributing to numerous multidisciplinary projects. He has given numerous invited lectures and is author of over 100 publications in national and international scientific journals. In this seminar, Alfio Torrisi will present two microscopy systems optimized for soft X-rays and extreme ultraviolet. Particular emphasis will be given to the optimization of the experimental setups and to the results obtained by observing different biological samples. It will show how remarkable efforts have been made to improve the spatial resolution obtained through different types of microscopy. In particular, the employment of complex sources based on the soft X-rays and extreme ultraviolet production has made it possible to overcome the limit imposed by large facilities, which needs to deal with several requirements such as an expensive maintenance, high complexity, and limited access. The gas puff sources, based on the employment of double gas flow, developed at the Military University of Technology of Warsaw, represent a valid tool for transmission microscopy, allowing to obtain a nanometric spatial resolution higher than that obtainable with traditional optical microscopes. The title of the seminar is Microscopy Techniques Based on Gas Puff Target Sources. Please.
Good evening. Thank you. Thanks for this kind presentation. I thank Professor Carcanile to give me the opportunity to present one of my research topics today. And this is developed in collaboration with the Military University of Technology in Warsaw and the Czech Technical University, and is related to microscopy techniques based on gas puff target sources. So I will show you briefly the outline of the talk. I will show why we are motivated, interested on develop these laboratory-based soft X-ray and extreme ultraviolet sources for microscopy. I will show the feasibility of a source based on a double-stream gas puff target for this purpose. I will explain to you in detail what does it mean, a double-stream gas puff target. Then I will go to the core of the presentation, which is related to design and development of such microscope, and I will show the setup, the characterization of the source, the resolution estimation, in the end application and imaging results, and then conclusion and achievements. So we know that recent rapid development of nanoscience and nanotechnology require nanometer scale resolution imaging tool and methods to investigate the matter, so to investigate inorganic samples and even organic ones. So we can investigate from the macro to the subatomic scale, but in this case, for this presentation, we are interested into the nanoscale range. In general, we know that according to the Rayleigh criterion, once we reduce the wavelength for our investigation, we can increase the spatial resolution. So for the visible light microscope, we can investigate on in the range of the wavelength between 400 to 700 nanometer. But if we want to go into the nanoscale, and in particular in the short wavelength range, we can investigate tens of nanometers. But why we are interested in soft X-ray radiation, and what is the water window imaging? In general, soft X-ray are radiation included in a range between 124 eV and 12.4 kV, but exists a particular range inside this bigger one, which is called water window, and is between 2.3 and 4.4 nanometer, which thanks to the different absorption coefficient of element which limited this range, it means oxygen and carbon, allow to have a natural high contrast for biological imaging. Then we can even improve the spatial resolution, and we have the good penetration in micrometer thick samples. Instead, we are interested in extreme ultraviolet radiation because in the range between 10 and 124 eV, which is the range of this EUV radiation, we can have a good optical contrast due to the atomic resonance frequencies. We have high absorption in very thin layers, and we can observe even microcrack in thin materials. Moreover, this range is important and interesting because of several applications in lithography. For instance, using the wavelength of 13.5 nanometer, we can use this wavelength for investigation in mask inspection. So we know that over the world exist different very bright facilities, which are very large facilities as well. Large, it means that even if they are bright and they allow to have a high number of photons and they are tunable in let's say, in energy, they present some drawbacks, it means some disadvantage, because this source has limited access, as we know. Is necessary to book your time to perform your experiment, so you have to plan in advance your investigation. Then the sources are high, very complex and costly, and maintenance is expensive as well. So from this comes the necessity to use laboratory sources in order to perform experiment in a small scale, and to have quickly to have results. So, for instance, if we mention the laser target interaction, we know that exists one. I show you two of the main laser which operate with the same principle of interaction of laser with the solid target, but they work in different way because, of course, the pulse duration, the energy, the power is quite different. But I want to show you this because this is one of the possibility to perform experiment in small laboratories. One of the disadvantages of this source, as well of other sources, are that, for instance, for the solid target, we have the production of debris. So all the time you perform experiment, you can have a certain number of shots, of laser shot, and then after that you need to open the chamber, clean the chamber, and restart with new measurements. Other possibilities to perform experiment in laboratory environment, for instance, are capillary discharge, which was used and is used as well in different laboratories for imaging, but in this case the lifetime of the capillary is very short. So it means that it is time demanding to acquire good quality images. As well, this is another Another kind of source is a droplet source used in Berlin, for instance, even in other laboratories in Europe and around the world. But in this case, the particularities and the difficulties stay in the necessity to collimate the drop with the ion beam. So you have to create the drop and then to synchronize the drop with the ion beam is quite difficult. So these are some of the examples. From this example, in the early 2000s, come the necessity to develop some new kind of source with a new approach in order to have something which should be easily accessible, user-friendly, with a low cost of operation, compact and usable indeed in laboratory environment. So a group of Professor Fedorovich in the Institute of Electronics, which I still collaborate, they create the first kind of UV soft X-ray lamp for metrology, and then was used for microscopy and even for other kind of experiment. So this source works as I will show you in this slide. We have a laser beam which is focused with the proper lens inside this vacuum chamber. Inside the chamber there is a double stream of gas. Why we have a double stream of gas? We have a double stream of gas, for instance, the working gas is a gas which should have higher Z number respect to the other gas. And the particularity of this source is that if we use outer gas and working gas, as we can see from this shadowgraphy, we can observe that thanks to this property, to these characteristics, we can have the possibility to direct along the nozzle direction emission the gas, avoiding the spreading of the working gas itself after few millimeters from the emission. In this way, we can have a high number of photons which can be used then for not only for imaging but even for other applications. And I will show you better in the next slide one example. So the source is used in Institute of Electronics for different applications, as I mentioned. I was and I am still involved from time to time to microscopy application, and as I mentioned, the source is very compact, and because of the main particularity, which is a debris-free source, you have the possibility to have thousands of shots per day without the necessity to open, clean the chamber because of the debris and so on. So you can have a good set of measurement in the same day or of images, because you can collect image in a very short time. Moreover, you can of course change the gas and you can filter the radiation with the proper filter in order to get kind of quasi-monochromatic radiation. For instance, in the case of the soft X-ray microscope, we use 2.88 nanometer as wavelength. This is the emission of the nitrogen, and we cut the other emission thanks to a self-standing titanium filter 200 nanometer. This is just the scheme of the microscope, how it works. It is quite simple as a mechanism, because at the beginning we can see here the first part of the setup I showed a few slides earlier. And we have the laser target that hits the gas path, producing plasma. In this case, we use nitrogen plasma, and at the proper pressure. Then this plasma radiation is collected through a particular optics, which is called ellipsoidal condenser. After that, we find the titanium filter, and after we have the sample, the diffraction lens we use, that is a Fresnel zone plate, and which allow to assess the radiation in the soft X-ray water window range. And then we have the CCD camera. Generally here we can see what I mentioned before. We use the nitrogen radiation emission, but thanks to the 200 nanometer titanium filter, we cut almost the radiation, the peak at 2.4 something nanometer, employing almost only the radiation at 2.88 nanometer. For this reason, we say that this is a quasi-monochromatic radiation. This is how the microscope looks like in the laboratory. The optical type dimension are 1.8 times 1.2 square meter, and we have here the small chamber of gas path. Then this is connected with the microscope chamber. In the of course, behind there is the pumping laser, the Dino-Yag laser. But inside the microscope chamber, there are the real, let's say, optics which are used for our experiment, for imaging, of course. So instead, before start to acquire images, we characterized the source in terms of plasma distribution, in terms of plasma size, and more important is that we can collect at this wavelength 8 times 10 to 9 photons per pulse. And usually we use as a repetition rate of the laser 10 Hz. So the first image results, in order to define the resolution of the microscope, was acquired with a commercial TEM mesh, which is a well-defined period. And in this way, with the so-called knife edge test, we were able to determine the half pitch spatial resolution, which is the range between 25–75% of intensity transition across a sharp edge. And in this case, the half pitch spatial resolution for this microscope is equal to 60 nanometer. And here just I show you a quick comparison how the mesh looks like with the visible microscope with the soft X-ray microscope. We can even see a sharper defect of the mesh itself, and we can achieve even we can even spot 200 nanometer defect inside this sample. This image was acquired with the 60 nanometer resolution, 220 as a magnification. Then we started to acquire some image to demonstrate that the microscope works. So we started with an organic sample. This was one of the first example. This regards show silver nanowires on 30 nanometer silicon nitride membrane. Silicon nitride membrane. Silicon nitride is a good material which allows to observe in transmission. So usually you will find in this presentation different time this silicon nitride membrane because we used to have liquid samples we took just a liquid, a drop of the sample, we deposit it on the membrane, and then after it was dry, we acquired the images. And this was another example. Still, we are in organic field. This regards gold microcrack, because this came after chemical treatment for thermal stress and rapid cooling generate microcrack, and in this case we can observe even small features approaching 100 nanometer if we enhance the contrast of the image. Of course, these are all the image collected with the normal visible microscope. Soft X-ray are the images acquired with the developed microscope. Then we started with biological samples in collaboration with other institutes. This first sample regards DNA plasmid. Plasmid is together with DNA can be inside the bacterium. In this case, this supercoiled plasmid was observed as after 500 pulses, and it means after only 50 seconds of acquisition at 10 Hertz. But in this case, because of the high concentration of carbon, we can't observe inside the plasmid, but we can just see some small dots. And the smallest one looks like we can achieve, in this case, we can resolve up to 200 nanometer. This was another example of a particular algae. In this case, we know from the reference that these are symbiotic microalgae, and they looks like green and with some flagella in the end. So they are like a couple. We have a couple of these algae and the flagella in the end at the beginning, like here. But if we observe the image with the visible microscope, we can barely see the sample itself. With the soft X-ray, in the end, we are able to have a better contrast and to observe the some of such flagella. But one of the more important results we got in collaboration with the Czech Technical University, which prepared for us the sample, regards this mus musculus fibroblast colon carcinoma from mouse. In this case, after 62 seconds, 600 shots, it means soft X-ray pulses, we could observe very small features approaching the resolution of the microscope itself. This is another sample of the same kind of carcinoma. In this case, we can distinguish better few features approaching even 240 nanometer in the soft X-ray field. And this, in collaboration with the Paul Scherrer Institute, was prepared from them. We observed, this is an image in false color, different dendrites of some neuron cells. Of course, this is an approach to demonstrate more that the microscope, it is working, is a potentiality, but to have more information about biological side of the sample, we need even to collaborate with other institutes to have feedback from them as well about what we observed. It fits because they are really dendrites, and here we can observe a sharper image of the neuron itself. Of course, to acquire good quality of image, behind there was a study of the noise and how to increase the signal to noise ratio, because the source of noise are different and we can only reduce the noise, but we can't completely eliminate it. So here briefly I show some of the source of the noise. There was performed a long set of images to have to write a paper about it, but here just I mention two of the best conditions to take into account to acquire good quality images. The conditions are related usually to the laser, to the CCD properties. In this case, if we change the temperature of the CCD camera, so acquiring with as low temperature as possible, so cooling the camera as high as we can obtain a higher number of soft X-ray pulses. And for instance, for single shot operation, still was made a study taking care of the binning pre-processing of the image. In this case, we can obtain higher SNR, signal to noise ratio, as lowest is the readout speed of the CCD camera. Was made even a collateral study related to plasma diagnostics using particular detectors, because usually we use silicon carbide detectors, but we wanted to test in collaboration with the University of Messina even some detectors, so-called silicon carbide with interdigitated contact. In this case, in this way, using these detectors, we can have a different advantage. We have a higher band gap with the SiC versus the silicon one. We can have noise reduction, radiation hardness, high electron mobility, and then we have a very high density of electrons and holes near the interdigit collector zones, in which the active region is limited to 4 micron in depth and to 3 micron in the electron width. In particular, just to mention something about this side work, was studied the quantum efficiency of the detector at the wavelength used for microscopy imaging, 2.88 nanometer. And here just I show you how the signal rise, increasing the pressure of the employed gas, in this case nitrogen. Here just another comparison between the silicon and silicon carbide detector. In this case we can see, for instance, that for silicon carbide detector we have longer signal, but we have higher intensity and higher signal, high detection efficiency in the field of soft X-ray. And of course, silicon carbide cut visible and extreme ultraviolet radiation emitted from plasma, enhancing the sensitivity to very fast ions. But going back to our microscopes, after we characterized and we studied how to acquire image in 2 dimensions, we tried to improve the microscope in order to acquire 3-dimensional images. So in this case we used the same setup, but for the holder we create ad hoc 2 kinds of holder which can rotate, and as we can see here, there are one tip holder in this case, we can use some grain to put on the tip, and then by rotational, we can acquire image at different angles, and then reconstruct the image. Sorry. Or we can use, as we made before, the silicon nitride membrane that looks like that, and we have a particular holder with the slit. We put the silicon nitride membrane in the holder, and then we rotate here, as we can see, acquiring at a different angle still the images. We used these particular stages with nanometrical resolution in translation, and we started the experiment as usual. It means that, first of all, we acquire image in the visible with the normal commercial optical microscope, so the visible light. Then, because the field of view, of course, of the soft X-ray system is different, we select some region of interest. In this case was this part, and then we scan at a different degree the same image, trying then to reconstruct the image itself. So these were some first experiments trying to see what we could get. Still is tricky get internal feature of biological sample, because we need to not have a high concentration of carbon inside the sample. But this was a didactic example of the tomography system, which I would like to show you. Basically, if we go back and we see this image, it seems a normal image, as usual. But if we scan a different angle, starting from 9 degree, 12 even, we start to see this break, this crack, let's say, of the membrane. Then, if we reconstruct with a 3D projection the image, we can observe here the damage. We can that was first out of plane. Then, due to this, we can clearly observe. Another starting example come with this algae. Still, we made the same. We started to reconstruct the projection, but the next example was more interesting, because this example allows us to determine the voxel size of the system. So we used not the slit holder, but in this case we used the tip holder in order to deposit some grain of caffeine, and then to acquire first with the SEM the grain, and then acquiring the image with the soft X-ray at a different angle. Here we can see rotationally how the grain looks like. And in collaboration with the Faculty of Mechatronics of Warsaw University of Technology, then it was possible to make not only the image reconstruction of the grains, but even with this particular algorithm reconstruct the grain in 3D and determine the voxel size, which is like a pixel in 3-dimensional way. That is 320 times 320 times 320, so cube nanometer. This was the first kind of microscope, which was even improved as a tomography system, but another much more compact prototype of microscope, in this case operating in the extreme ultraviolet range, was developed. This is much more compact, as we can see. The dimensions are here reported, And the mechanism, and it is made similarly even to the previous one, but in a small scale, because we have here the neodymium laser, which is focused in the gas path target source. Then we have a molybdenum silicon ellipsoidal condenser instead of the previous optic, which was a different condenser. And then here, which is reported here on the bottom right side of the slide, the real component of the microscope. So this is the scheme. These are the characteristics of the laser. We can achieve 10 to 11 photons per pulse at the wavelength we used, which was 13.8 nanometer. We characterize the source as well, and we determine with the knife edge test the half pitch spatial resolution, which seems even better than the previous one achievable with the soft X-ray. In this case, we have 48 nanometer. I show you some results. In this case, CT26 cells imaged in the visible and in the extreme ultraviolet. Here we can solve a few small features of around 100 nanometer. Here something going behind is almost 50, so achieving almost the resolution of the microscope. And here some comparison. This was a comparison very nice, because as I mentioned before, we are interested to observe something inside the biological sample. So diatoms allow us to do it, and this is a very nice example to see what we can observe with the free kind of microscope. So with the soft X-ray, we are able to see something sharper than with the visible light. But if we go to the extreme ultraviolet, we can even resolve very small feature of about 60 nanometer, even in a smaller time, because here there is another example of this algae. Here we can see that with the extreme ultraviolet we can gain in contrast, and you can acquire this image in a shorter time with less number of shots. It means of extreme ultraviolet pulses. In this case, 100 versus 5 times more for soft X-ray. So, just to try to make an overview of the system, I presented you something that is somehow innovative as a laboratory environment and versatile. It allows to achieve a resolution between 50–60 nanometer with the short acquisition time, and can be used in a multidisciplinary environment, and why not can be even commercialized in the future. Of course, it needs to be improved, because the number of photons is still limited, and the repetition rate as well, if we compare it with large facility, free electron laser or synchrotron, as I mentioned at the beginning. And even the signal-to-noise ratio can be improved. Most of the improvement come even from the diffraction lens from the laser we can use. For instance, just to have an idea how our microscope are accessible and quick to use, I mentioned two kinds of microscope which are used in other nice, very important laboratory in Europe. The left one in Sweden, the right one in Göttingen. They allow to observe with very high resolution sample, but for this compact. Let's say this microscope is not really compact because as drawbacks it takes few optical table, and the source, which is based in a cryojet target, is quite complicated. Instead, if we go here on the right side, this compact source in Göttingen is a very compact source, but to acquire a good image, you need 1 hour and 800,000 pulses. And then the spatial resolution is still comparable with what we can get with our setup. This is just a final comparison showing some advantages and disadvantages of our microscope. Because still, sorry, if we look at the table, we have as advantage of, if we compare our soft X-ray and the UV resolution, which is better for sure of that obtainable with optical microscope. Of course, is not comparable. Is lower than what we can achieve with STID microscope or SCM, but it presents some other advantage because it doesn't need. They don't need to work in high vacuum as it happened for SCM, and they don't need a particular preparation or treatment of the sample. So, in conclusion, based on the results I show you, I try to let's say, present this work and how it is possible to prove that a laser plasma incoherent source based on a debris-free double-stream gas path target can be employed for development of experimental water window soft X-ray and for technology demonstrator of extreme ultraviolet microscopes. Such microscopes bring very important aspects like the desktop size, fast exposure, nanometer spatial resolution, and these microscopes can be used, of course, not as substitutive but as complementary imaging tools to already existing well-established ones, providing additional information about the sample we would like to investigate and making possible wider collaboration in a multidisciplinary context with biologists, chemists, scientists from other universities or companies. These are some of the publications I was able to let's say, some of the work I was able to publish over the time related to the imaging system and to the silicon carbide detector. Some of them are open source, so if you would like to know something more in detail, you are free to download or just ask me if you are interested to do something else. And I would like to thank you all the partners of this collaboration and even all of you for your attention. Thanks.